Okay, on page 7 of your notes, 576 for the textbook, it talks about what if we had a reaction that has two reactants. So far, all the work we have done has been with just one reactant. You know, all the calculations we have done, one reactant. But what if we had two reactants? If we have that happen, it is called a pseudo first order. Well, hold up on that part. A pseudo rate law. And all that means is we manipulate the reaction. Like, I don't know, let's say we have A reacts with B to form C. We got two reactants, right? Well, obviously it's going to be extremely difficult to obtain data for two reactants at the same time. So what we do is we will make one of these concentrations very, very large. Like, for example, concentration of A, if that's the one that if we want to determine data based on A, like if we want a rate equals K, A to the, whatever order, then what we would do is we would make the concentration of A very small, relatively small, and then we would make the concentration of our other reactant B very large. Very large. That way, think about it. When that reaction starts, and we start it starts consuming A and B. Any change, if you've got a small concentration for A, any change in that's going to be significant, right? But let's use an analogy real quick. Remember back in thermo we had this one analogy. Let's say we give $50 to a broke college student, and we give $50 to Bill Gates. Y'all know who that is, or Donald Trump. Okay, we give $50 to a college student. We give $50 to Donald Trump. In which one is it going to be more significant? College student. Why?
They got the money.
Yeah, they don't have much to begin with, right? They might even have less than $50 to begin with.
They have to make it.
But Donald Trump,
a small loan of $1 million.
Right. But if we give $50 to Donald Trump, yeah, I mean, he probably gives that as a tip to, at lunch. He probably gives more than that as a tip at lunch. So do y'all see the difference? So think about this. If we have the concentration of A really small, and then the reaction starts, and A starts getting consumed, right? Changes in it are going to be significant. Do y'all agree? Okay, if we start out with a lot of B, and let's say this is a 1-to-1 mole ratio, okay? Any changes in B, since compared to A, B is huge. So any changes in B are going to be insignificant. So this A would be the college student, B would be Donald Trump. You see what I mean? So when we do that, that allows us to manipulate the rate law in this way. Listen carefully and do not let this mess you up. The actual rate, let me erase that for a second. This would have an actual rate law of rate equals K, A to the nth order, B to the nth order. Agreed? Okay. But since we are manipulating it, we are trying to find out, let me get my highlighter. We want to know that, right? We want to know that. So our rate could also be described as, well, this and this would be equal to something called K prime. That little mark right there means prime. Just means a different K, a different value for K. So we could say K prime is equal to K times B to the nth order. Okay? It just means a different K. And then we could express rate equal to K prime A to the nth order. This is called a pseudo rate law. Pseudo means fake.
Yes, so chemistry teacher, your calculus.
I'm sorry.
I said you're sneaky with your calculus.
I'm sneaky with my
placed in
calculus.
there.
So it's K prime, or is A to the nth power?
So it's like K prime is equal to this and this.
Oh,
We're not measuring it, right, because we're keeping B very large. So we're not going to be able we're not going to have any appreciable data for this. So we're going to redefine our rate law to make it, the whole point of this, y'all, is to make it easy on us in the lab. That's the whole point of this stuff. This is what you will apply in your kinetics lab. You're going to react a substance called crystal violet. It's used as an indicator solution. You're going to react it with sodium hydroxide with a hydroxide ion. We're going to keep the hydroxide ion concentration very, very large and make the crystal violet concentration really, really small. And that way, any data we get will be related directly to crystal violet, which will be our A in this case. And this is just a manipulation so that we can ignore that second reactant. That's all this is. Are y'all good with it? Am I going to ask you to derive this? No. You won't even see this in free response. You will have like a definition of pseudo rate law in multiple choice. Pseudo rate law is defined in your glossary. It is explained on page 576 and in your notes, and it's honestly no more than what I just put on the board. It's just a way to make it easier to deal with data in the lab. That's the only reason for this. You will apply it in your lab.
would we be giving K prime?
Yeah, we'll be able to get all that in. All the information we need, we'll be able to obtain somewhere. Because the only thing we're going to be, think about it, when we do our lab, the only thing we're going to be able to use is concentration and time data. So that means from that we'll obtain an integrated rate law, and then we'll write the differential rate law from it. We're going to use a device called a colorimeter, and it measures something called absorbance, which is how much light a chemical absorbs. The more concentrated it is, the more light it absorbs, the higher your absorbance, and it's a direct relationship called Beer's law, and we will be able to use it to get our concentration data, and then we'll use, your stopwatch for your time data. And then from that, we will calculate K. So you're good, okay? No worries, we good, right? Moving on. page 8 of your notes. Page 579 of your book. Reaction mechanisms. Remember at the beginning of this last week, we talked about how a reaction doesn't necessarily go directly from A to D, or A to B, I think is what I said. Oh,
Isn't that
hello. Oh, you're cute. Thank you. I should. Okay. A to B. Well, it's not necessarily A to B. What it might actually be is A makes C, and then C might make D, and then D might make B. Yeah. Right? So if you combine them, just, like we did with Hess's law, if you just combine them, look what happens. C gets produced in one step and gets consumed in the next step, right? And then D gets produced in one step, but gets consumed in another step. They cancel out, right, on paper. So when everything's all done, we end up with A going to B, right? That's how most reactions really happen. We obtain rate laws, and from that, we can figure out this stuff. Or we might be able to use this stuff to come up with a rate law. This whole thing here is called the reaction mechanism. The reaction mechanism is a series of steps that occur to yield a chemical reaction, a chemical change. Okay? All right. These things that I circled, or that I crossed out rather, they are called intermediates. All of these terms are in the glossary, they're in the reading, their definitions, and in the notes. An intermediate is, something that gets produced in one step and consumed in another, and that's it. That's all it is. So, this thing here is called an elementary step. This thing is called an elementary step. And guess what that thing's called? The whole thing combines to make the reaction mechanism. Okay? This thing right here, ooh, that thing, this thing is called molecularity. Not all of them. This, let me re-highlight. Let's do it. Yellow shows up better. That. Molecularity is simply, I'm going to erase this out. Get some space. Number of particles. On reactant side. Just fancy word. So instead of saying number of particles on the reactant side, which is like, what, 4 words, they just call it molecularity. I mean, honestly, you know. Okay. So that's all the parts. That's all the parts of this stuff, right?
So C, B, and B don't have a fancy name.
On the right side, we don't even look at, remember, in any of this stuff that we've done in kinetics, we don't pay any attention to the right side of the arrow. Like I said, that's there. We only remember, ever since we came back from Christmas, we have only looked at the left side of the arrow. That's all we do with kinetics. It is. All right, so what do we do with this stuff? We can use a reaction mechanism to predict a rate law. We can use a reaction mechanism to produce a rate law, but there's some criteria that it has to satisfy for a reaction mechanism to be possible.
Sorry for the interruption, but not trying to high girls and they depend for pictures.
Instead of possible, we might say plausible. Have y'all heard of that word before? Okay, let's use that word. Did I spell it right?
I think so.
Okay.
That's plausible.
That was very funny.
Okay. Okay, y'all listen to the words coming out of my mouth. Okay, for a reaction mechanism, which is a series of elementary steps, to be plausible, it has to satisfy 2 requirements. This is on page 9 of your notes. Midway. We'll come back to the top of page 9 in just a second. The sum of the elementary steps must give the overall balanced equation for the reaction. Like we did here.
No.
You know, like this right here. You add up all the steps, cancel out intermediates. You got to end up with the overall reaction. If you don't, throw that mechanism out. It's not it. The second requirement, the mechanism must agree with the experimentally determined rate law. We're not going to do mechanisms in the lab. This will be purely academic. You will have it in college. Again, you will see this again. If you take, I think it's analytical chemistry, which is called quantitative analysis at ASU. I don't know what they call it at U of A, probably analytical. Okay. Take a look at the top of page 9. Here's what they mean by the mechanism has to agree with the experimentally determined rate law. If you have an elementary step of A goes to products, how many A's are there? Just one, right? We could, this is weird, and I don't know what to tell y'all other than to accept it and go on. Okay. We're going to write a rate law from the mechanism. And then that rate law that we write from the mechanism has to agree with the one that you determined with data experimentally in order for that mechanism to be plausible. Okay, so here we only have one reactant and it's A. So the rate law that we would write from that mechanism would be rate is equal to Ka. What if we had that? How many A's are there? So rate equals Ka, 2. Now, one of y'all might be thinking right now, wait a minute, last week she told us that we cannot get the reactant order from the coefficients in the balanced equation. Do y'all remember that? Well, it's true, you can't. You only get the reactant order from experiment. But this is a prediction. This is not written in stone. We're saying, could this be a possible mechanism for this reaction? You write a rate law based off of the steps, and if that rate law matches the experimentally determined rate law, then it might be a possible mechanism. That still doesn't say for sure that it's the mechanism. It's just a possible one. So it's a whole bunch of ifs is what this stuff is. Y'all all have these case looks. It's not hard. And I know some of you are trying to think very carefully to figure out the nuts and bolts of this and understand it. And I'm telling you, just accept it and go on. Okay? Unless you are going to do research and development work, you're probably beyond the classroom, you're probably not going to have to worry about this. Okay? Now, if you are, pretty much that's it. Doctors might need to, and pharmacists would need to understand it when they read it, but it's the folks, the doctors and the pharmacists in research and development that are going to come up with this stuff. Are y'all okay now? Does that kind of put it in perspective? Okay. All right. And if we have then the predicted rate law would be rate equals K. How many A's are there? How many B's? Then you would check this against your experimentally determined rate law. If it matches, this is a possible mechanism. And we're about to practice this. Okay, I'm just introducing it right now.
On that, could you use the K1 too, or would you just write it out like that?
Say again.
Could you use K1 on that, or K prime, whatever it's called, on that? Or do you have to write it out like that?
You have to write it out like this, yeah. The only time we use K prime is if we're dealing with pseudo rate laws. Let me finish this and I'm going to go back to pseudo rate law in just a second. And then what if you had that predicted rate law would be rate equals K A squared, and then you would check that against the experimentally determined rate law. Okay, some new terms, some new vocabulary. How many reactive particles are here on this first one? So we call that step is unimolecular. And how many here? Guess what it's called? This step is bimolecular. What about this one? Bimolecular. And what about this one? Yeah, instead of try, chemistry uses TER, organic chemistry especially. This is called TER molecular. TER and try means the same thing. Look at the bottom of your notes, page 9, next to the last entry. Can't stress it enough. We can never prove in the lab, on paper, anywhere, we can never prove that a mechanism is definitely the mechanism for that particular reaction. All we can do is say that it's possible. So how do we use all this stuff? We determine the rate law with experimental data first. Then we kind of use what we know to come up with steps, and then check to see if those steps combine to get the overall equation and a predicted rate law that matches the experimentally determined rate law. We are not going to do that in here. If you are a research chemist in your future, that's what you do, okay? We simply don't have the time to explore stuff like that because that would take months, weeks or months of research to come up with. We just don't have it. Y'all good so far? All right. Remember all those steps in a mechanism? Remember all the steps, right? They can have different speeds. Each step has its own rate, right? Which one is the rate determining step? The slowest. That is the third from the bottom on page 9. The slowest step in a mechanism is the slowest step. The overall reaction will never happen any faster than that slowest step. So it is the rate law from the slowest step that we are interested in as far as predictions are concerned. Billy? Let me say a couple things for you, Lee. Right here, pseudo rate law. What if that reaction were first order? We would call it a pseudo first order rate law. Y'all get it? What if it was second order? Pseudo second order rate law, blah, blah, blah. Okay. I would like for you to do this for me, for yourselves. I would like for you to please answer number 10, number 12. That's it. And I'd like for you, that is page 597. And then I would like for you to read section 6, section 7. That's a lot. That's a lot. And I'm trying really hard to keep us on schedule, but I don't think we are ready to start a kinetics exam tomorrow. So tomorrow, let's just push, can we push the kinetics exam to Monday? All right, so we will do lab first period, kinetics, collision model, and catalyst tomorrow, and Friday, second period. All we have left in kinetics, catalyst, collision model, activation energy. Collision model and catalyst are qualitative. Activation energy is qual and quant. Okay? Then we'll be done. All right, y'all have a good rest of your day. Thank you.
What is your, next one?